Okay, so let's talk about some material that we should remember. Now, indefinite integrals we didn't talk about for a few days, but I think it'll come into play today. So they're back. So what are indefinite integrals? Well, they're essentially antiderivatives. So remember, an antiderivative of a function, say little f of x, is a function capital F of x, so that when you take the derivative of capital F, you get little f. So the antiderivative, or if you like, the indefinite integral of x to the a dx is 1 over a plus 1, x to a plus 1, plus, of course, an arbitrary constant. So antiderivatives differ up to a constant. So that's why we always have these plus constants on the end. Now, I will say, I'll warn you, if on the final you do have an indefinite integral, make sure you remember the plus c and make sure you remember the dx. Because if you don't have those down, we can take off points for that. These are very important concepts. So be careful with your notation, especially when you have 3 hours. Maybe if you only had an hour, we could be a little bit less forgiving. But when you have 3 hours, make sure you get everything in, the plus c's and the dx's, if they're indefinite integrals. Well, you always get the dx's in. The indefinite integral of sine is negative cosine. The indefinite integral of cosine is sine. And I mean, how do you check? Well, very simply, you say, well, what's the derivative of sine? It's cosine. So that's how you can see there's a relationship. The indefinite integral of secant squared is tangent plus constant. Indefinite integral of secant tangent is the secant plus the constant. And, of course, one of my favorites, the indefinite integral of 1 over 1 plus x squared is arctangent plus a constant. So those are the indefinite integrals. And then last time we started talking about what are called definite integrals. And since they only differ by the I and the n, you probably think there's a lot in common. In fact, there is. Now, what are the definite integrals? How are they defined? Well, we define them by saying we take these Riemann sums. The idea is we chop up what we're looking for to lots of little tiny slivers, little tiny pieces. And we say, well, let's say we're looking for area. We'll think of it as an area. What's the area of each little piece? So the area of each little piece is something like the FCI delta XI term there. And then to get the whole area, we add them all up. Now, of course, when I look at FCI delta XI, that's really just an approximation. So we get better and better approximations by letting this delta XI, the width on the bottom, go to 0. So if this converges, whatever it converges to, we call the definite integral from a to b of f of x dx. Now, the nice thing for our class is that every function we're going to encounter will be integrable. In other words, we can integrate, find this definite integral. Now, what kind of functions can you do this on? Continuous functions. Any continuous function, you can always do it. If you have a function with just a few jump discontinuities, you can do it. And there are other functions as well. But for us, mostly for the moral for us is that continuous functions, you can always do this. And how do we interpret this? Integral from a to b, f of x dx, which is, I guess I should say, that's how we read this notation. Whenever you see this long s stretched out, that's the integral sign. Integral from a up to b of the function f of x dx. So how do we interpret this? Well, this is a signed area between the curve y equals f of x and the x-axis, from x equals a to x equals b. So in other words, I have my curve here, y equals f of x, and I'm going from x equals a to x equals b. And I'm looking for the area. So I have some area here, I have some area here, of course I have some area here. And the trick is if I'm above the x-axis, that's positive area, or it will contribute a positive value to my sum. If I'm below the x-axis, we think of this as negative area, and it will contribute a negative value to the sum. And similarly, this will be positive, and it contributes a positive value to the sum. All right. That's the definition, some intuition. Let's go into some more details. So what are some definite integrals that we know? Well, the integral from 0 to b of 1 dx is very easy. It's just b. Yes, you have a question?
For the signed area, like if you were to calculate the area under the curves, would you have to like split it up into pieces or something?
Well, when you're calculating the signed area, the technique that we'll learn today, it'll automatically do it for us. We don't need to worry about it. Now, that's if you can do what we're about to do today. I don't want to give it away. there's about to be this like big denouement. I'm like building up to this massive structure, saying, "Oh, really? We do call them the same thing because they are in fact the same thing." But I don't want to give that away yet. But if you can do the antiderivative, it's automatically built in. Now sometimes I'll give you a function. So when you sometimes will see problems on test, like I taught 3B last year. And the way I did it was I defined a piecewise function using some very basic shapes, like a flat lines, and maybe a circle. And in that case, you can say, well, maybe I should also have some negative area in there as well. If you have something like this, well, then what you can do is you can say, I know how to interpret this integral, even if I don't know exactly what this antiderivative is. Even if I can't do the indefinite integral, I might still be able to do the integral from a to b, in which case, yeah, you just break it up and you use knowledge of geometry to figure out how each individual piece is, and you combine them together. And in fact, that's one of your homework problems is you'll have a problem where it'll draw a basic shape using some figures like circles and straight lines and say, find the definite integral. And so you just use, I know some geometry. No problem. Okay, so what are some definite integrals that we know? The integral from 0 to b of 1 dx is b. The integral from 0 to b of x dx is a half b squared. The integral 0 to b of x squared dx is a third b cubed. In fact, we can change these a little bit. Instead of going from 0 to b, we could go from a to b. So integral from a to b of x dx is a half b squared minus half a squared. Integral from a to b of x squared is 1/3 b cubed minus 1/3 a cubed. And it took us a long time to find these. And we spent almost a full lecture just trying to figure out what this is. And as you can imagine, it gets harder as you get more complicated functions. And so we're going to try to find a way to more easily get to that. And in fact, by the end of today, this will be so easy that we're going to be like, give us a real challenge. It's too easy for us. But before we get to that, let's talk about more properties of definite integrals. One property is that if I have two functions adding together, and I want to integrate from a to b, I can basically break it into two parts. So it breaks up over addition. So the indefinite integral of f of x plus g of x is the definite integral of f of x plus the definite integral of g of x. Same bounds on both of them. Similarly, I can pull out a constant. The integral from a to b of a constant times f of x dx is that same constant times the integral from a to b of f of x dx. So we've seen these two properties now numerous times. We've seen these with derivatives, and we've seen them with indefinite integrals, and we've seen them with definite integrals. These are actually very nice properties, and they're called linear. It says that definite integrals behave linearly, so you can break it up. The definite integral from a to a of f of x dx is 0, and that's a very easy picture, because if I go from a to a, I essentially have 0 width. So there's no area. Of course it's 0. The integral from a to b of f of x dx is minus the integral from b to a of f of x dx. So in other words, if you change the order of integration, so in other words, you swap top bottom, you need to make sure to get a negative sign in there. The integral from a to c of f of x dx plus the integral from c to b of f of x dx is the integral from a to b of f of x dx. So the picture for that, intuitively say, okay, well, here's a, here's c, here's b. Well, the integral from a to c is this area. The integral from c to b is that area. And, of course, the integral from a to b is that area. And it's really easy to say, well, of course, if I add these two areas together, I get the total area. But one of the things I didn't tell you is I didn't tell you how a, c, and b are related. So, of course, it's easy to see it in this case. But what if they're related in a different way? Suppose I have, here's a, here's b, and here's c. Then what do we have? Well, the integral from a to c is this area, and the integral from from c to b is this area here. Does that equal the area from a to b? Well, let's think about it for a second. So the integral from a to c, it has the right order, or as I would call it, the right orientation. Usually we like to go from the low number to a high number. So that's good. A to c is fine. What do we know about the integral from c to b? It's essentially going in the wrong direction, because usually we like to go from the low value to the high value. So normally what we would do is we would actually swap. So that the integral from c to b is actually, think of this as the negative of the integral b to c. So that's the same as the integral from c to b. Losing space. So because of the order, this in fact becomes a negative, and then you'll say, aha, so if I take this total area, subtract out this area, then yeah, in fact, that is the right thing. So it doesn't matter how a, c, and b are related. This always works. All right. Let's talk about some other properties that we might like to have. Okay. So suppose that f of x is less than or equal to g of x on the interval a less than or equal to x less than or equal to b. Or if you like, that's the same as saying ab. So I have two functions, and I always know that f is underneath g. So picture-wise, I have f on top, I have g on the bottom as I go between a and b. Well, what's the relationship between the definite integral from a to b of f of x dx and the definite integral from a to b of g of x dx? Well, it's not too hard to see. The integral from a to b of f(x) dx is all this area here. And the integral from a to b of g of x is just the area down here. So that, in essence, this area up here is the excess. How much more f is, how much bigger f is compared to g, as I look at the definite integral. And, in fact, we have this nice inequality. So if I have one function below another function, and when I take a look at their definite integrals, I still get the same inequality going on. This is not surprising. Now, be careful. The opposite isn't true. Just because the integral from a to b of f of x is less than or equal to the integral of a to b of g of x does not mean that f is always less than or equal to g. Because what can happen? Well, what can happen is you can have something like, let's see, what do I want? I want f to be, so maybe I can have f be something like this, and then I can have g of x do something like this. And the area underneath the curve f of x, in this case, the area underneath the curve f of x is pretty small. And the area underneath the curve g of x, I actually get a lot of excess up here. Well, anyways, not the prettiest picture, but just be careful. I think as one of your TA says, A implies B is not the same as B implies A. Now, as a special case of this, we have the following. Suppose now I have some constant m, little lowercase m, is less than or equal to f of x, and uppercase m is greater than or equal to f of x. Again, between a and b. Well, then what you can say is that if I look at the integral from a to b of f of x dx, what happens? Well, I can just apply this on both sides. In this case, f of x is less than or equal to m, so this is less than or equal to the integral from a to b of capital M. But what's this integral going to be? Well, the m is a constant, so it comes out in front. So I can pull constants out. So essentially, it's m times the integral of, if you like, 1 dx from a to b. Now, fortunately for us, this is an integral we can actually do. We actually have it written down here. The integral from a to b of 1 dx is simply b minus a. Because essentially, if you think about the picture, it's just a rectangle. So this is m times b minus a. On the other hand, I can apply the same inequality on this side. So this is greater than or equal to the integral from a to b of lowercase m dx. And I do the same trick, if you like. Factor out the lowercase m. And they say, well, that's an easy integral. That's m times b minus a. So now we have this equation. And of course, I like to write it in a slightly different way. I like to say that this implies that m is less than or equal to 1 over b minus a integral from a to b of f of x dx is less than or equal to uppercase m. And we'll use this fact in next lecture, Friday's lecture. So you can use this to find some nice properties. So for instance, an important integral you're going to learn about next quarter is the integral of 1 over x. Suppose I want to get an estimate for the integral of 1 over x for x from, say, 10 to 20. I don't need to know the exact value, but I need to know ballpark range. What should this be? So an upper bound and a lower bound. Well, I can think about my function 1 over x. Looks something like this. Let's say here's 10, here's 20. So what do I know about the function 1 over x between 10 and 20? Well, what's the largest value it takes? Well, the largest value it takes between 10 and 20 is at 10, because it's a decreasing function here. So I know that 1 over x for x between 10 and 20 is less than or equal to a tenth. What's the smallest value that it could possibly be as I look between the interval from 10 to 20? Yeah, it's over at the other end. It's 1/20th. So I know that 1/20th is less than or equal to 1 over x is less than or equal to 1 over 10. And now I can use this to say I can either use this fact here or this one, either way. So the thing this is my lowercase m. Here's my f of x. Here's my uppercase m. So then I have 1/20th is lowercase m times b minus a is less than or equal to this integral, which is 10 to 20, not a to b, which is less than or equal to capital M, 1/10 times b minus a. And we can clean this up. 20 minus 10 is 10 times 1 over 20, so this is a half. Is less than or equal to the integral from 10 to 20, 1 over x dx is less than or equal to, and then again, 10 times a tenth is 1. So whatever this value is, the integral from 10 to 20 of 1 over x dx, it's somewhere between a half and 1. And next quarter, you'll learn the exact value for that. All right, so let's see, what else can we do? Here's a fun problem from the homework. Let's think about it. Suppose I ask the following question. What's the integral from negative 10 to 10 sine of x cubed times x to the fourth cosine x plus 7 dx. So suppose you saw this kind of question on the final. Now, those of you who've taken this class before, you might think, oh my gosh, this is going to be painful. And you'd be right if you try to actually do it. So let's try not to do it. Let's try to think about it. Now, I look at this function here, and I say to myself, this function is kind of peculiar. Indeed, I would probably go so far as to say that this function is kind of strange. Or some people might even say that this function is kind of weird. Or some people might say this function is kind of odd. It's an odd function. Wait a second. Odd? That has a meaning. What does odd mean when I talk about a function? Okay, not even. Yes, that's a good definition. Odd is not even. Yes. That is, well, it's not quite true for this case. An odd function is a function when you plug in the negative value you get negative f of x. So f of negative x is negative f of x. Well, let's see what happens when I plug in negative x. So if I take negative x and I cube it, I get negative of x cubed. Now sine is an odd function, so sine of negative x cubed is the negative of sine of x cubed. And then again, sine again is an odd function. So when I start with the negative x here, what will happen is I'll pull out negative in front. Now on the other hand, if I plug in a negative x to the fourth, I get back x to the fourth. Cosine of negative x is cosine of x. Cosine is an even function. And in 7, of course, there's no x. So this is an odd function. Now, what do we know about odd functions? We know that it has this fact. What does that say about the shape of the graph? Well, it says whatever it does over here, it'll go through the origin. You can check, plug in 0, you get 0. Whatever it does over here, I don't know. It does the exact opposite over here. So I don't know what the graph is, but I do know that it behaves in this exact sort of, whoops, sorry, maybe it's going to be over here. It behaves in sort of this exact opposite manner. In particular, whatever the value of the area is over here, what's going to be the area over here? It's going to be the same but negative. So what will the integral turn out to be? 0. It's one of these fun facts. So if you have an odd function, you can sometimes save yourself some work. Now, of course, you have to realize that it's an odd function. They're cruel in their homework. They didn't give that to you as a hint. But fun things you can do. Now, it only works with odd functions. With even functions, you don't get that same cancellation going on. All right. So I think now we're ready to start talking about why we have these things called definite integrals and indefinite integrals, and they're the same thing. And that is the fundamental theorem of calculus. But in fact, the fundamental theorem of calculus is so important, we decided not to have just one fundamental theorem of calculus. We decided to have 2. So we're not going to do both of them today. Today we'll do part 1, the first fundamental theorem of calculus. And the first fundamental theorem of calculus says if a function f of x is continuous on the interval a less than or equals x less than or equal to b, and capital F of x is any antiderivative of little f of x, then the definite integral from a to b of little f of x dx is equal to capital F evaluated at b minus capital F evaluated at a. And there's another notation for this, by the way. Let me write it down. This is also known as f of x evaluated from a to b. So this is the first fundamental theorem of calculus. Now, what's the idea here? We've done 2 kinds of things in calculus. We've looked at derivatives, and we looked at integration, or integrals. The fundamental theorem of calculus basically says, lo and behold, there are 2 sides of the same coin. They're related. So, in particular, if I want to know the integral from a to b of f of x dx, I really just have to figure out what's an antiderivative of this function, little f of x. And once I do that, it turns out it's a really ridiculously easy problem. If I have an antiderivative of little f of x, boom, I just evaluate it at 2 points, and I'm done. So I don't care what happens at the endpoints now for the antiderivative. I don't need to worry about what happens in between. That somehow the antiderivative incorporates all this information is a very nice fact. So this notation, you will see it from time to time. So whenever you see this bar, we've seen it once before, it basically means you're doing some evaluation. We did it before when we talked a little bit about implicit differentiation. Here, it just means that you're going to evaluate from A up to B. So you plug in the top value, subtract, plug in the bottom value. So let's see how easy this makes some of our problems. So for instance, we spent a lot of time doing the integral from a to b of x squared dx. Let's see how fast we can do it now. So here, this is our f of x. And we say, OK, what's an antiderivative of x squared? Yeah, what's an antiderivative of x squared is 1/3 x cubed. Now, notice I said any antiderivative. So we know that 1/3 x cubed is an antiderivative. And so according to this, I take 1/3 x cubed, an antiderivative of what's inside, and I evaluate from a to b. Or I take 1/3 b cubed minus 1/3 a cubed, and let's check. Oh, it's the same. Notice how this was faster, though. It didn't take us an hour. And in fact, let's see how good we are. Suppose I ask what's the integral from a to b of x to the 4th dx. Well, again, that says that this function inside f of x is x to the 4th. So what's an antiderivative of x to the 4th? Now, 1/5 x to the 5th. Because to find the antiderivative of x to the 4th, if I'm looking for an antiderivative of x to the power, I add 1 to the power. So I have x to that new power, and then I just divide by whatever that new power is. So in this case, it would be x to the 5th, and I divide by 5. So it's 1/5. So this is 1/5 x to the 5th, evaluated from a to b, which is 1/5 b to the 5th. So I plug in b, subtract 1/5 a to the 5th, where I plug in a. Much, much faster process. OK, so this is examples, and we'll do some more as we go along. Now, you do have to be careful about this, I should point out. Function has to be continuous on the interval a less than or equal to x less than or equal to b. Now, why is this important? Well, suppose your function isn't continuous. What's a very simple example of a function that's not continuous? Well, suppose I ask for the integral from -1 to 1 of 1 over x squared dx. OK, so let's put this in quotation marks, because this is a bad example. Well, what's the integral of 1 over x squared? Well, we think about it. Think of this as the same as x to the -2 power. So if I function f of x is x to the -2, what's an antiderivative of that? You'd add 1 to the exponent. So -2 plus 1 is -1. And then I would divide by -1, which really is the same as putting a negative in front. Or if you like, that's -1 over x. So this is -1 over x evaluated from -1 up to 1. Let's see what that is. So this is -1 over 1 minus -1 over -1. Which is -2. Now, is -2 the right answer? Well, let's see what the picture of 1 over x squared looks like. The graph of 1 over x squared looks like this. And I'm going from -1 to 1. So I'm looking for this area. So should this area be -2? No, it shouldn't be. In fact, this area blows up. It has infinite area. Now, what's the problem here? Why doesn't it work? Our problem is we have this vertical asymptote at 0. It's not continuous. So to use the theorem, make sure we deal with a continuous function. So just be careful. OK, so continuity is important. But we're going to always ask for continuous functions, or we'll make it clear that it's not continuous, and then we'll know how to deal with it. All right. So that's the fundamental theorem of calculus. Let's see if we can prove it. So how do we prove it? Well, we think about what's going on. I want to relate these two quantities. I want to relate the quantity f of b minus f of a with this definite integral. Well, how do I think of this definite integral? This definite integral looks like a Riemann sum. So if I can make f of b minus f of a look like a Riemann sum, where, again, I can take a limit as n goes to infinity, then they have to match up. So that's going to be the idea of our proof. All right, so we have y equals f of x, and I start from x equals a, and I go to b. Now, what I'm going to do is I'm going to basically chop this interval from a to b up into little pieces. They don't all have to be equally sized. You can be if you want. And I'm going to label them. Now, a, I'm going to call this x0, then the next point x1, x2, so forth and so on. I'm going to get to what I call xi minus 1, xi. And at the very end, I get b, which is xn. So if you like, I basically broke up this interval from a to b into n little subintervals, or partitioned it into n pieces. All right. Now, let's look at f of b minus f of a. Well, because of my notation here, this is really the same as f of xn minus f of x0. Because I just said, let's call b xn, let's call a x0. I mean, that's nothing yet. And then we're going to employ a really cool trick in math. This is one of those really cool, like, wow, that's so cool. How would you have thought of that? Here's the trick. I'm just going to add and subtract stuff. So I'm going to start with my f of xn. I'm going to subtract f of xn minus 1. But of course, I didn't have an f of xn minus 1 term in there before, so I need to cancel it out. How do I cancel it out? I add it back. I add f of xn minus 1. Now I'm going to subtract f of xn minus 2. But of course, I didn't have an f of xn minus 2, so I need to cancel it out, so I add it. And I just keep going. And at some point, I'm going to have f of xi minus f of xi minus 1 eventually. And I keep going. And at the very end, I'm going to have an f of x1. And then I'm going to subtract f of x0. But I already had an f of x0, so I'm OK. So I don't need to do anything to cancel that term out, because that was already there. So there's the f of xn, there's the minus f of x0, and everything else cancels out. You might call it telescoping or collapsing. All right. Now, why is that useful? Well, let's think about f of xn minus f of x0. So f of xn minus f of x0. Oh, sorry. Sorry, I meant to say I and I minus 1. F of xi minus f of xi minus 1. So I want to just look at sort of a typical term. What does that look like? Well, now we're going to pull out a nice fun fact, which is the mean value theorem. So let me just write that down. It says if our function is continuous on the interval from a to b, then we have that the derivative at some point between a and b is equal to f of b minus f of a over b minus a. So that was the mean value theorem. So if I divide this by xi minus 1, so think of my xi as b, xi minus 1 is a. So according to the mean value theorem, this is going to be equal to f prime at what I'll call c sub I, where ci is between xi and xi minus 1. Okay, so far, nothing very surprising in the mean value theorem. But what is capital F prime? Where did capital F come from? Capital F of x is the antiderivative of little f of x, and so f prime is little f. I should say big F prime is little f, ci. So what does that tell me? That tells me that capital F xi minus capital F xi minus 1 is little f of ci times what's in the denominator on the other side, xi minus xi minus 1. But we had a name for this thing. What is that? It's how much we changed in x. The change in x we also called our delta x. And just to really abuse notation, I apologize for this, but I'll call my delta xi, a change in the ith interval. I'm really abusing notation, but you understand what I mean. It's the width of the ith interval. So that tells me that this f of b minus f of a, which I just rewrote here, and then I add and subtracted thing, each one of these little pieces here, this, for instance, becomes f of cn delta xn. This becomes f of cn minus 1 delta xn minus 1. And just all the way down. So this is f of your ci delta xi, and keep going, you get to f of c1 delta x1. So in other words, f of b minus f of a is equal to the sum I equals 1 to n of f of ci delta xi. Where ci, I don't know where ci is for any particular interval, but I always know that each ci lies in the right place. Each ci is on this ith interval between xi minus 1 and xi. The important thing to recognize is that this is a Riemann sum. So in other words, we've made capital F of b minus capital F of a look like a Riemann sum involving the little f, where I'm partitioning the interval between a and b. And of course, as I get a better partition, as I choose n larger and larger, as I force my width to get smaller and smaller, the Riemann sum will converge. It will always converge. And it doesn't matter which Riemann sum you use. It always converges to the same thing. So now I just let n get large and make sure my widths get small. What happens to this? It converges to the integral from a to b of f of x dx, but of course, I set it up so it's always equal to f of b minus f of a. And then we're done. Yeah? Yeah? Okay. Wow. Don't worry, you're not going to have to reprove it. Just remember that it works. And we're happy. Okay. So now we have this wonderful fundamental theorem of calculus. And now we can start doing all sorts of great integrals. Things that we would have been too intimidated to do before by chopping up into pieces and doing the sums. By the way, I'm not going to ask you about sums on the final. So I'm not going to have you find some limit of Riemann sums. Because we have better techniques. Why would we use that if we have a better technique? We wouldn't. It's crazy. So before well, yeah, let's just start doing things. Okay, so we already did x squared. We already did x to the fourth. Let's go back, fill in a gap. Let's do x cubed dx. And I'll do it from a to b. Now, I'm doing this for a specific point. I just want to point out something here. Not that it's going to be very enlightening compared to what we've already done. So this is, again, our f of x. F of x is x cubed. So what is capital F of x? Well, 1/4 x to the fourth. So I said use any antiderivative. Well, why can I say any antiderivative? Well, let's find out. I know what the antiderivatives of x cubed look like. They look like 1/4 x to the fourth plus a constant c. So I could have chosen c to be anything. Usually it's just convenient to choose c to be 0. But you don't have to choose c to be 0. You can just choose c to be anything you want. So what happens if I choose c to be 0? Well, simple. So this is 1/4 x to the fourth plus c evaluated from a to b. So I'm going to keep the c there and see what happens to it. So this is 1/4 b to the fourth plus c, subtract 1/4 a to the fourth plus c. So I just plug it in, and then a plus c comes along each time. And now, lo and behold, what happens to my c's? 1/4 b to the fourth plus c, subtract 1/4 a to the fourth, subtract c. You'll notice that the c's exactly cancel out. The plus c and the minus c. So that we get 1/4 b to the fourth minus 1/4 a to the fourth, which is what we would have gone if we just started with 1/4 x to the fourth. So that's why it doesn't matter which antiderivative I use. Because any antiderivative will differ by a constant, and when you do the subtraction, the constants always cancel out. So that's why we always just say, well, just choose c to be 0. But you don't have to. You can choose it to be something else. If that's like your signature, it's like, okay, I'm just going to be cool, and always, every time I'm going to choose c to be 8. I'm going to be known as Mr. 8. You can do that. That's okay. You'll still get the same answers. All right, now let's do some practice. Suppose, this is one we probably couldn't do before. I asked for the integral from 0 to pi of the sine of x dx. So sine function looks like this, and in fact hits the x-axis at pi again and keeps going. All right. Well, what I need is I need an antiderivative of sine. Do we know an antiderivative of sine? So an antiderivative of sine is negative cosine. So it's important to get the signs right, otherwise you'll be off by a negative sign. Oftentimes if you're off by a negative sign, Okay, so it's negative cosine x evaluated from 0 to pi. So that is negative cosine of pi subtract negative cosine of 0. What is cosine of pi? Cosine of pi is negative 1. So this is negative of negative 1. Subtract, and cosine of 0 is 1. And now you have all these negatives. Those two cancel out. Those two cancel out. So you really get 1 plus 1 is 2. All right, suppose I ask the integral from 0 to 2 pi of sine x dx. Now, without even doing the integral, what's the answer? It's 0. Because you can see there's this nice picture here where this area, of course, exactly cancels out that area. So, of course, we should get 0. But we can check it out. We get negative cosine x, a value from 0 to 2 pi. It's the same thing we're integrating, so it's the same antiderivative. So that's negative cosine of 2 pi. Subtract negative cosine of 0. Negative 1, subtract minus 1. And you see they cancel out. We get 0. Okay. And we'll do some more next time. Okay. Have a good day. So I do have office hours this afternoon, and of course on Friday morning if you have questions.